Okay, so now this is the second video on Thales's theorem of proportionality. But before we actually get to the theorem, I just want to continue from what we finished in the last video, which was that if you enlarge a figure, if this is my original figure, A, B, C, D, E, F, I'm not in the right order, if this is my original figure, and if I say I want to enlarge it with a factor of 2, then what do I get? And with this O as a centre d'homothety, center of homothety, then I will draw these lines. I've drawn only for 3 points, A, C and D, but you get the idea. And if I say 2, then I take OA and then I mark on the same line OA prime. I mark A prime, which is twice OA. OA here, OA prime over OA has to equal 2. I do that with all the others, OC, OC prime, OD, OD prime, and then I can draw the figure. If you can see the squares on my paper, this line is 2 squares, and you see this line is 4 squares. This line is 1 square, this line is 2 squares, this line is 3 squares, this line is 6 squares. So the figure has become double. Another interesting aspect of enlarging using a center of homothety or reducing, if we had reduced it, then the figure would have come here, a tiny figure here, is that the corresponding sides are always parallel. So AB is parallel to A prime B prime. Similarly, say D is parallel to say prime D prime. If I draw on a diagonal line here, C E, that would be parallel to say prime A prime. This is an interesting property. It follows from what we will see later. It is the theorem de Thales, the proportionality. Okay. The reason I am repeating all this is that you can have k as a number that is also negative, in which case it goes to the left. So if I say k is minus 2, then the same thing I have to do on the left side. So OA I take, and then A the prime I put on this side, where OA prime divided by OA is again 2. So I have written it here. OA prime, pardon, O the prime, no, OA the prime sur A, sur OA est égal à OB de prime sur OB, OC de prime sur OC, O est égal à O de prime sur OE, OF de prime sur OF est égal à 2. So here also you see OA de prime divided by OA is 2, OC the prime divided by OC is 2, and basically you have a figure again which is twice the size. So that means this figure here is the same as this figure here, only it is rotated. It is rotated. And again, if you see, the lines are all parallel. This line is parallel to that line. The line is parallel to here, the line, and if I drew a diagonal here, this line would again be parallel to this line. So these corresponding lines are parallel. This is the only thing I wanted to say about this, because here we have introduced a concept of k becoming negative. When we did chapter 10 on enlargement and reduction, agrandissement et réduction, there we had said k can only go from 0 to positive. K cannot become less than 1. So if you see in the book, you don't have it for much longer, the book, except if you're out of town, I guess. So this on page 158, this is the first thing, homothety. So here is the normal if k is bigger than 1, and here you see it comes back to the left, AB and AB prime. Here they have taken rapport k est égal à 0,1 moins 0,5. Here they just took line BC, which they wanted to enlarge. They didn't take an entire figure. Here also they've just taken line BC. Here is K est égal à 3. So AC prime sur AC est égal à 3. Here they have AC prime sur AC est égal à moins 0,5. They use moins because it is going in the opposite direction. Okay, so that is all that I have to say about this. And now we come to the theorem de Thales itself. I have written it out nicely here somewhere. Let me find it. Yes. And now, because you will not have the book, I will want you to copy this page, this whole page. You can pause the video and you can copy it in your notebook for reference, because this one page contains all the information you require to use Thales's theorem of proportionality. Now, Thales was one of these famous Greek mathematicians from older times. He actually lived 2,600 years ago, and here, for example, this chapter is called Utiliser le théorème de Thales. But he has many theorems, and this is not his most famous theorem. So we should always call it Thales's theorem of proportionality. This book just calls it Theorem de Thales, but if you Google Theorem de Thales, you will get some other more famous theorems that he discovered. So, what does this theorem say? This theorem says, if two lines BM and CN, these are lines, remember, curved brackets, intersecting at point A, if two lines BM and CN, so here we have BM and CN, they are intersecting at point A. Yeah, this is clear. Don't look at the figure on the right. Look at the figure on the left. BM and CN, they intersect at point A, are intersected by two parallel lines base A and MN. So basically, if you have two lines like this which intersect, that means which are not parallel, two lines, any two lines, and they are intersected by two parallel lines, by two parallel lines base A and MN. If you have this, then this is the theorem de Thales. This is what it says, that these ratios are all equal. It's a bit similar to what we were just discussing with the agrandissement réduction, but this is a formal way of saying the theorem de Thales. If two lines BM and CN intersecting at point A are themselves intersected by two parallel lines MN and base A, then these ratios are all equal. What are these ratios? AM sur AB. Yeah, this will be in this case less than 1 because IM is smaller than AB. They are saying is equal to AN is equal to AN over AC. Here AN over AC is equal to also MN over base A. Now this is a theorem de Thales. There is a proof for it also, and depending on how much time there is, I will actually provide you the proof. The proof is just 2 pages long. It proves this equation, and it also proves other 5 variations of this equations, all of which can be actually be derived from this. So let me find it in my notebook. This is in my notes for the previous class that I had done. I had actually done more than the thing. This is the thing. Here, of course, I've numbered them differently. Instead of MN, I have DA. So if DA is parallel to base A, and I also have this line parallel to this line, then you get 6 equations: 1, 2, 3, 4, 5, and 6. This is the equation that we saw in our book. And these are only the reciprocals. AD sur AB, we made it AB sur AD. DB sur AB, we made AB sur DB. So basically 3 equations, and these are the reciprocals. That is, they are flipped. But anyway, we will not look at this. The proof, you can see, goes from here, and It goes here, it proves 1 and 2, then you go a little bit more, it proves 3 and 4, then you go a little bit more and it proves 6 and 5, and it also you can also then finally get 5 and 6. These are 5 and 6 partially, these are 5 and 6 the complete thing. Anyway, I will see whether I will give that to you. At the moment, let's come back to our theorem of proportionality. See this page, you can pause and copy. Now, so we have seen A and B is the line here. M is between A and B, but it could also be in a different order. Lines B and C, Mn parallel. You could have Mn below with base A above. Here Mn is above and base A is below. So even in this case, this equation holds. Here Im sur AB, Im sur AB. That means Im sur AB is more than 1 because Im is longer than AB. And similarly, In est égal à In sur AC, which is also more than 1, est égal à Mn sur base A because Mn is also longer than base A. But these ratios will be equal assuming Mn is parallel to base A. And then a third example of the same thing where base A is on this side of the A and Nm is on that side. Remember, this is not M and N but N and M because N, A and C are aligned. A and C, A, C, N, A and C, N, A, C. Even in this case, this equation will hold. Okay. So, and the corollary means the consequence of this theorem is if two lines BM and CN intersect at point A, it applies to all three variants of the drawing, and AM over AB is not equal to AN over AC, then you can say MN and BC are not parallel. So, not only if BC and MN are parallel, then this is true. But if you find in a drawing that this is not true, that means BC and MN cannot be parallel and are not parallel. That's what we say here in the corollary. So, if two lines BM and CN intersect at point A and AM over AB is not equal to AN over AC, then MN and BC are not parallel. Okay. By the way, Thales was a Greek mathematician who lived around 2600 years ago. Okay. So now we take a few examples of what we can do with this theorem. Okay. So let us see. I again draw this. Mn is parallel to base A, and I give you the Thales equation. I rewrite it, I copy it again so that you don't have to scroll back in the video. Okay, so if I say if AM is equal to 2 centimeters, AN is equal to 2.6 centimeters. Please note that these numbers are not, this figure is not to scale. So these numbers, if you try to print this image out and measure it, it will not be correct. And AB is equal to 3.8. What is AC equal to? So basically we are giving you this dimension, this dimension, this dimension, and we want to find out this dimension, AC. AM is equal to 2 centimeters, AN is equal to 2.6 centimeters, AB is equal to 3.8 centimeters, AC is equal to, that is what we have to find out. Okay, so let's start. Let's take just this part of the Thales's equation. Forget that last part. So we write AM over AB is equal to AN over AC. Here what don't we know? We don't know AC. We know an, we know ab, we know am. So this is basically fractional with where one value is not known. It's very easy to solve. The first thing is we multiply both sides by ac and divide both sides by am. So basically we put ac there and we put am in its place. So we'll get ac over ab is equal to an over am. I'm sure you know how to get from this point to this point. We are multiplying both sides by AC and we are dividing both sides by AM, which in effect comes to replacing AM by AC and replacing AC by AM. So we're just exchanging these two. So now we have that. Then we multiply both sides by AB. AB gets cancelled out here. Basically we take this and multiply it there. So we get AN into AB over AM. So we say 2.6, AN is 2.6. AB is 3.8, AM is 2. When you solve this, you will get AC is equal to 4.94 centimeters. So basically, given three of these dimensions, you can get the fourth one. Okay, let's take another case. Again, this time I have drawn it in that way where A is in the center of B and M. And lines NM and BC are parallel, BC and MN are parallel, and this is the theorem of Thales, which I have just copied here again so that we don't have to scroll back. So here if I say AB is equal to 3 centimeters, this is AB equal to 3 centimeters, AM is equal to 5 centimeters, AM is equal to 5 centimeters, AC is equal to 1.8 centimeters, then what is AN equal to? Now in this case I want to find out AN. So we have this, we just take the first two terms, we get AM over AB is equal to AN over AC. Let's just switch them. So I write on the left AN over AC, this I write on the right AM over AB. AN is already there. So AC we multiply this with AC, AN is equal to AM over AB into AC. We replace the values, 5, 3 into 1.8, AM is 5, AB is 3, AC is 1.8, and we'll get the answer AM is equal to 3 centimeters. Okay, so you've got the hang of it, basically. So, now the first problem for you. This is the problem you have to do. You don't have to draw it to scale in this particular case, because this is a calculation problem. Later on we will be doing some problems where you will have to draw it to scale with proper scale and ruler and correct measurements. But here, okay, so I have this, base A it is parallel to MN. This is given, base A is parallel to MN. AB is equal to 2 centimeters, AC is equal to 1.9 centimeters, AN is equal to 2.8 centimeters. What is BM equal to? BM. Now if you go back here, you will see that there is no BM. There is no BM here. So it's a little tricky. How will you calculate BM? BM is only from here to here. So the tip is calculate AM first. If you calculate AM, then you should be able to get BM very simply. This is problem number A that you have to do. And this is problem number B. So in this particular case we have the same configuration as here. Here AB is equal to 1.6 centimeters, again not to scale. AM is equal to 2.6 centimeters. AC is equal to 1.4 centimeters. AN is equal to 2.4 centimeters. You see, in this case I did not say BC is parallel to MN. Here I am giving you all four measurements and I am asking you, are BC and MN parallel? So the answer to this problem will be either yes or no, and you have to use the theorem of Thales to show it. You know, this is the corollary that I had mentioned earlier. If two lines intersect at point A and this is not true, then MN and BC are not parallel. So here you have to see whether those ratios are correct, whether this ratio is correct. AM over AB is equal to AN over AC. If this is correct, then BC and MN are parallel. So this is a 20-minute video. It's almost 20 minutes. So we will stop here, and tomorrow I will post another video, a short video on the reciprocal of theorem de Thales, which is very simple here. This is the theorem de Thales, which basically says if this ratio is correct, then the two lines are parallel. Exactly what we were seeing here, what I've asked you to do. But this is known as a reciprocal of the theorem de Thales. Okay, so let's stop here. You send me these two answers to these two questions. Very simple. It's mainly to see that you have understood. And very importantly, yes, this I forgot to tell you, or I did, but you should, I'll repeat that this particular page, Thales's theorem of proportionality, this page you should copy out, especially because you will not have the book any longer. Okay, I will stop here and we will continue tomorrow or day after.